What's going on, guys? It's the Unhinged Engineer back with episode 7 of my grad school vlog. So if this is your first episode with us, welcome. To catch you up to speed, I am pursuing a Master's of Computer Science with a focus in perception and robotics at Georgia Tech as part of their OMSCS program, while I continue to work my full-time job, which is as an AI/ML researcher in the aerospace and defense sector. So yeah, I'm trying to juggle my job, plus school, plus my YouTube channel, and just make content for other like young engineering professionals trying to like make their way and figure everything out, right? Because I don't know about you, but it's a little bit overwhelming once you get out of school. And so if that's the kind of content you're interested in, welcome to the channel. Please like, comment, and subscribe. And in today's episode, I'm going to talk about the second project of my first class. So my first class is on AI techniques for robotics applications, which is convenient given my specialization. And this project I'm going to talk about today is on particle filtering. Okay, so the first one was on Kalman filters, and the second is on particle filters. And this kind of chunk of the class in general is about localization techniques, so like Bayesian estimation, the things I just mentioned, and a couple other peripherals, right? And I'm going to have a midterm on those topics pretty soon. But today I'm going to focus specifically on the project. Yeah, let's get right into it. So, to give up a bit early, I didn't enjoy this project as much as I enjoyed, the Kalman filter project, right? Like, I don't think it was bad. I think I did learn a lot, but it was more frustrating than the first one with less reward for a couple of reasons I'll talk about here. But before I do that, before I just start venting, let me describe the project. So the central problem that we're trying to solve here is we have a satellite orbiting the sun, and there's a bunch of other planets orbiting the sun. And so your visualization basically just looks like the solar system, or a solar system. And using measurement information, you're supposed to estimate the position of the satellite that's in orbit. So you're trying to estimate your own position. So you don't know where you are, but you are taking measurement readings and using those plus particle filtering in an intelligent way, which I'll describe in a moment, you can localize where you are. So how does that work, right? Put briefly, the way that the particle filter works is you spawn in a bunch of particles in the simulation that behave identically to you. So at each step in time, they all move in the same way. In our case, it's like a counterclockwise orbit, okay, of a constant radius. Your radius isn't changeable. So all of them propagate in motion the same amount. Okay, and you're gonna take a measurement both from yourself and from every particle. And what you're doing is you're saying, okay, even though I don't know where I am, I know my own measurement that I'm taking. And so if a particle's measurement is dramatically different from my own, it's probably not near me. It's not near where I am, okay? And so what you do is you set up a Gaussian distribution about your own measurements, not position, measurements. And if a particle is outside of a certain like standard deviation of the likelihood of getting that measurement if they were in the same position as you, then you kind of chop it, right? And you don't actually chop it. What you do is you set its weight very low, and then you do a weighted resample of all those particles, meaning that when you do these resamples and you're kind of copying over old particles with new ones, the ones that are less likely, based on that Gaussian distribution, are less likely to be resampled. And then over time, over enough time steps, all that's left is the particles that converge towards your position, right? And then eventually you get an estimate of your own position. And that last estimation step is just like, take the average position of all of them. Because if you get a little cluster around your own position, and then you take the average, it should be there, okay? There's a couple of other peripherals there that I've kind of alluded to, mainly in regard to like fuzzing and noise, which I actually found to be the more rewarding part of this project, and I'll get to that when I get to like the positives, okay? Yeah, but fuzzing is essentially just adding noise. It's just adding a bunch of noise everywhere, and also like trying to bias things towards particles you want. It's kind of like jankifying the solution, which for something like a particle filter, which is very, very stochastic by nature, like that's kind of sometimes what you have to do, okay? But let's talk about some of the reasons, the gripes I had with this project. First thing I didn't really like was like the structure and the requirements for getting a certain grade. So the way it worked was you had to pass 75% of the test cases to get 100. So like in my case, I got 100 because I passed 16 of the 20 test cases that you go through. There's 10 test cases for part A and 10 test cases for part B. I just realized I forgot to mention what part B was, but essentially you just take that particle filter you used in part A and use it to like shoot a laser or something. And it's just like a little additional geometry. So I'm not really going to discuss it much for this, talk. But yeah, 10 for part A, 10 for part B. And if you get 15 out of 20 total, then you get 100. And obviously that's, good, right? Because I mean, some people got 100, like all test cases, but honestly, I'm shocked. Like that is so impressive to me because it was so hard to get mine performing adequately. And that was with a ton of janky crap that I'll describe in a moment. Sorry, somebody's playing music in my hallway and I wanted to make sure it didn't come up on the mic. Anyway, back to the video. Where was I? Oh yeah, so I didn't really like the structure and the requirements a ton because even though you only have to like pass 75% of test cases to get 100, passing a single test case actually has like very strict requirements. The main one I have a gripe with being the accuracy. Like your dot and the dot of your satellite have to be exactly on top of each other, like as exactly as you can imagine. For multiple time steps. So it can't like jitter at all around the satellite. Okay, so the accuracy requirements are super high. There's a time step limit in the simulations. You get like 300 time steps, which I never really had any problems with that one, and that kind of makes sense. But there's also a CPU time limit, right? So like your algorithm can't be so slow that it just takes forever. And the main reason they add that is that you don't just bombard things with particles. And I know that because like my minimum viable product for the project, like the first thing I had working, actually converged really reliably. But the only reason it did was because I like supplemented my lack of peripheral things like fuzzing for just like dumping a bunch of particles into it. And that slowed things down, and then, that's not something really usable, right? So I understand the value of all these constraints. Like I think, I'm gonna say this as a positive even though I'm complaining about it. Like it did illustrate the need for certain things and some of the trade-offs you have to make when designing these kinds of filters really well, right? But personally, I would rather a different approach where the requirements for passing a single test case are a little more lax, but then you have to pass more test cases overall, which is kind of how the common filter project worked, okay? And yeah, the reason for that is like, it's just very frustrating. Just like watching your particle or your estimate get so close to the satellite and then just getting no credit for the test case. Like it kind of sucks. Versus like, you get that dopamine hit of watching each one hit, but then you don't pass enough in the end to get the grade you want, right? And then also too, there's a little more variability in terms of like, well, on the Kalman filter, I got like a 93, I think, and I just kind of left it. I was like, whatever, I don't care, right? Versus this one, like you go from, 100 down to like an 80 pretty quickly, because that's only like 2 test cases. And so yeah, it's a little frustrating and nerve-wracking, but not a huge complaint. The other large complaint I had here was like, even though I really appreciated the solar system setup, like it was kind of a farce. Like it's really just a visual solar system, right? Mainly in 2 ways. Like the first way is we're just using basic like kind of bicycle motion. It's called the bicycle motion model to propagate all our satellites around this orbit. And like, I feel like most orbital mechanics formula, you can solve a lot of those with just basic algebra. And so I feel like doing that instead of this weird bicycle motion model that's usually intended for like land vehicles like cars, like it kind of broke the immersion a little bit, right? And this bicycle motion stuff's gonna be on the midterm, so I'm kind of stuck with it one way or another. But it was a little strange to kind of like have to just ignore the fact that we're working on a solar system. And maybe that's just me being like a pompous aerospace person. But anyway, the other thing I didn't like, and I think is a more grave issue, was like the measurement setup. So the way that you take measurements in the first part is you basically just get like a resultant of the gravitational force of all the different planets, right? So you're kind of like, I'm in a certain position and that position is relative to the other planets, and I'm experiencing a certain like gravitational pull in that position. And then you do that for all the other particles, and theirs are going to be pretty dramatically different from yours, right? The reason I don't like this is because usually with like particle filtering or SLAM or these kinds of state estimation techniques, like you have vector measurements, like measurements from each planet, right? And that gives you a lot more information, right? Now, I understand why they did the gravimeter, they call it. I don't even know if that's a real thing. Is that a real thing? Gravimeter to measure the net force, right? Like, they're trying to keep things simple. But it just felt, like, unrealistic. Because, you know, if you're doing, like, stereo vision, as an example, right? Stereo vision or LiDAR or these different things, like your measurements are always vectors. Like you're taking your measurement relative to multiple landmarks. Okay, so just kind of having one felt weird, right? It probably also saved me a bunch of time, so I shouldn't really complain, but it just felt unrealistic. Yeah, those are kind of my like nitpicks, but I don't think it was all bad. And I think the most valuable part of this project was the fuzzing, and that was a pretty rewarding part. Okay, so fuzzing, there's kind of like two ways that you do fuzzing. The first way is you add noise to the particle's position before you do the motion step. Okay, so just kind of like you all your particles jitter, because at each time step you impart some noise on where it is. And then the other one is you apply some noise to the motion step, right? So maybe some of them move a little further front, a little slower, or they turn a little bit less or more. Like you're just adding randomness into the particle filter. And that was neat, because it's like, you know, with the Kalman filter, you're relying on linear algebra and statistics, right? I mean, you're relying on that in this too, but I'll get to my point in a second. Like, you're relying on linear algebra and statistics and good measurements, right? Good measurements and good predictions, so that it ultimately converges to what you want. With the particle filter, like, you want randomness. Like, you want to inject a bunch of entropy into the process of resampling over and over and over again. And there's actually another form of fuzzing called prior editing, which kind of changes like how you resample too. So even on top of like taking that weighted Gaussian and then having a certain likelihood, you introduce randomness again, right? So it was neat to have to do that, because it showed kind of the beauty of the particle filter. I thought that was cool. And also, like, fuzzing was something we didn't really talk about in the lectures, which at first kind of annoyed me, because I was like, oh, I have to go figure this out on my own. But, you know, this is grad school, and there was a moment of, like, going out and reading papers and looking at supplemental materials and talking to other students, and it was like, oh, okay, like, this was cool. I had to go out and figure that out on my own, right? So that was pretty neat. And the Kalman filter didn't really force you to do that as much, and this one did. So that was pretty cool. And then the other one was, like, I think they kind of knew that going out and doing these little, like, fuzzing things that we didn't learn about in the lectures is going to take a lot of time and a lot of forethought. And so they kind of give you the structure that you should follow for the overall algorithm, like, right up front. And again, this is different from the Kalman filter, because the Kalman filter, like, the structure and the order in which you do math is kind of like the part that they're trying to teach you. But for this one, like, the structure that we're given in the lectures is the structure that I want you to use for the project. And then, like, adding in, you know, how do you initialize your particles in an intelligent way? How do you do fuzzing? How do you change resampling? Like, those things, doing all that tweaking, they kind of leave up to you. So I liked that overall. I thought that was pretty cool. And then again, like, in terms of the instructors and TAs and everything, like, they were great. They held talks and stuff and office hours, answered questions on edX. Like, they did a good job as usual. So yeah, I mean, overall, like, I think the main takeaway from this was having to go out on your own and find this kind of information and integrate it into what you learned from the lectures. Like, that was an additional step that didn't really exist before for some of the easy problem sets and then the first project, right? So that was like a good lesson to learn. And I think for some of the more complicated ones coming up, I'll have to do that again. And then there was also kind of like a negative lesson of, like, even though I said the fuzzing is like intentional jankiness in your simulation, like, there was some actual jankiness just in terms of my software. And so I feel kind of like ashamed of my Gradescope submission, because it's just like so ugly. Like, there's like global variables in there, loop structure's god awful, like, variable naming's atrocious. Like I just kind of hodgepodge something together that worked. And obviously this isn't anybody's fault but my own, right? But, like, there was kind of a thing I learned where it's like, oh, well, since we're submitting everything to Gradescope, if it works, it works. And for this project, that was okay, but it almost caught up to me at the end. Like it almost hit a point where the technical debt the bell of technical debt tolled for me, right? And that was scary, but I got through this one, so I just have to be careful to manage that better next time. But that's just kind of a negative lesson that I learned. But yeah, I mean, I don't remember if I gave the Kalman filter project a rating, but if I did, it probably would have been like 8. I'm gonna give this one like 8 out of 10. I'm gonna give this one like a 6.5 out of 10. Like, it was good, but there's like some room for improvement and tweaking, and I didn't get everything out of it that I'd hoped. But I did get a lot, and it achieved its mission of teaching me about particle filters and forcing me to implement one, even if it was kind of a crap particle filter. But yeah, so on to the next one. There's actually the next project is going to be the PID project. That's like a short one that comes right after the midterm, and so the main thing I'm going to focus on for like next episode is the midterm. So I got a lot of studying to do, a couple of problem sets, but like I've said before, those are kind of easy. Yeah, that's basically everything for the particle filter project. Sorry that this one was a little bit of a ramble, but there's a lot to discuss, and I know I kind of introed the particle filter in the last episode, but there was just a lot to discuss that I didn't get into, and I want to give you all the whole lowdown if you're taking this class right now and you have to do the particle filter project. So yeah, do your fuzzing. It's mandatory. Do the fuzzing. But yeah, thanks a lot for watching. Like I said at the beginning of the video, I'm the Unhinged Engineer. I am an AI/ML researcher in like aerospace and defense, and I'm making content for young people starting their engineering career, continuing to go to grad school like I am. People basically just trying to like make their way and stand out in this hyper-competitive field that we call engineering and technology. So if that's the kind of content you're interested in, like, comment, and subscribe. Stay tuned, and I will see you in the next video.